Okay, hello everyone. Welcome back. Hope you all had a good start into the new year. So before we start with today's talk, some quick announcements. First of all, we're still fixing our schedule. So if you have some interesting paper you would like to present that you, for example, submit to ICML or so, please do reach out to us. But also, if you're interested in you saw a recent paper that you would really like to see in this seminar, please also send us an email. The second announcement, so thanks to Arbor, we also have now a LinkedIn channel, our LinkedIn account. So please do subscribe to that. And if you haven't subscribed to our YouTube channel or Twitter account, please do. With that, I want to introduce our today's speaker. It's Andreas Mueller. Probably most people know him. He gave a keynote at the AutoML conference, which was really great. And I'm pretty excited to have him here today to talk about this new stuff, MotherNet, which he didn't talk about during the AutoML conference. So this is like brand new. So yeah, with that, please join me in welcome Andreas. And Andreas, please take it from here.
Hey, and thanks for having me here. Yeah, so I'll talk about this work that, as I said, as you said, brand new on MotherNet, which is basically a Hypernetwork version of TabPFN. And so, I assume people are somewhat familiar with TabPFN here. And if you're not, please ask questions in between, and I'll try to give the background. A lot of the stuff is taken from TabPFN, but then with some extensions, obviously. There's something else I wanted to say, but oh yeah. Hey Jan. In particular, please read the paper. If you have any suggestions and find typos in the next 2 weeks, that would be really appreciated. Also, please feel free to interrupt me or write in the chat if you have any questions. Okay. This is like, I gave this to audience that was not familiar with TabPFN, so I'm going to give a very brief introductions on like the steps of how I think about it. So in classical ML, you take some part of a table, the training set, you build a model, then you use the model to make predictions on what animations are not working on your test set. And so you have training, taking rows of the same data set, you predict on the on new rows. So you have per task, you build one model, and then you use the model for each row to make predictions. The idea behind foundational models, as we're probably all familiar with, was you take lots of data, you train a very generic model, which we then call a foundational model or LLM. And then for a new task, you provide a prompt that either just has a task description or maybe some examples which allow you to do in-context learning. So, and that will give you an answer. So here you just train once, and the prompt gives you the context for each individual task. And so the way we arrived at this work was, well, can we use something like foundational model for tabular classification? Because, I care about tabular classification. So we started with doing things like GPT 3.5 through GPT 4 and see, okay, we have these new technologies. Can we actually use these to do tabular classification? And we can try, but there's like some very obvious limitations. One of the big ones is language models are really bad at tokenizing numbers, in particular the GPT family. Oh, I should have put a slide on this. The GPT family, the tokenization of numbers makes no sense at all. It basically takes like 3 random integers or something, 1 or 2. So like the way a number is encoded is very, very arbitrary. So it's very hard for a GPT model to learn to reason about numbers. You have this recency bias. So, the last rows it saw, they're the most influential, even though, they don't really are supposed to have an order in most IID settings. Encoding your dataset structure into text is not ideal. Actually, my friend Harsha, I think, did a bunch of work, and several people, I think, tried this out. But to get the best performance, you ideally repeat the headers for every row. So you say, for this row, I don't know, age is this, and gender is this, and so on. And that really limits how much data you can consume, because you create a lot of extra tokens just by trying to serialize the data into a format that the language model can prompt. And so all of this, the great thing about using large language models for this is they can understand natural text. So if you have categorical variables that are encoded in text, they have the potential to be understood and like real-world knowledge be applied. But yeah, so we have this benefit, but I think there's too many shortcomings to do this directly. I was really, really excited when I saw TabPFN, because I've predicted this to happen for several years. So this is obviously the work of Samuel and Frank and the team and
Noah.
Noah. I was
Noah,
like,
first author.
yes. But there also, there's Katharina is also on the paper, right? Well,
Yeah.
Yeah. And yeah. So the idea here is to train a foundational model just for tabular data. And so there are several things that I find really fascinating about this. So first, they trained it entirely on synthetic tabular data. And so that was like a big emphasis of the work, is like, how do we generate a synthetic data in a way that we can train a transformer model? Then there's like tricks how to can we do a variable number of features, a variable number of classes. And but at least in the original architecture, sort of you automatically get a permutation invariance with the rows, because you just, transformers are kind of permutation variant with respect to tokens by default. But usually you use positional encoding. If you just leave out a positional encoding, you get sort of the IID structure. Whereas in the original work, which is you essentially use the features as the embedding vector, though there's a linear projection. But so this was sort of really nice in terms of how it encoded the data. And so the way it works is you train your foundational model on a bunch of synthetic data. You get the model weights for your transformer model, and then you do in-context learning. It contains the training set and the labels, and also the test set. And you can think of these together or as like the few shop prompting, where few is like a couple thousand training set examples, and the test sets are sort of the actual prompt, and you get the test set predictions out. And because it is trained specifically for the structure of tabular data, you don't have all the tokenization problems. You don't have to deal with making things into natural language, and it's a much more efficient way to work on numeric data. Also, you have a very different prior, which is a prior over that is given by the synthetic data generation process. So I was like, okay, this is amazing. And yeah, I really thought that this would come out of either DeepMind or OpenAI. So kudos, Frank. I was like, when I was working on scikit-learn, I was like, someone will make a transformer that will just do it. And then they did. So it's really cool because there's no training per data set. So you have, if you look at the combined training and prediction time, or something that we look later on at is tuning, training, and prediction time, because ideally we want to do something like AutoML. So, or whenever we want to do ML, we need to tune our model, like hyperparameters, do training and prediction. This is sort of, if you are in a data science loop, what you need to do to get your first result, to check if the model is working, if the features are good. So this combined time is quite important, of training and prediction, or tuning, training, prediction. Yeah, no hyperparameter tuning, while being competitive with AutoML, is obviously really great, because it makes it much easier to use, not only faster, but also you can just throw your data at it and it works well. And in particular, the prior is really useful for working, there's a typo here, with small data sets, something that a lot of traditional models struggle a lot with. And so there's a lot of small data sets out there in the world, and having good performance on this is really great. The cons for this approach is that because you have no training, that means the prediction time, if you get a new row that you want to predict on, is very slow compared to traditional methods. And so if you want to deploy the model, it's kind of, there's some things that are nice about it. It's nice about it that you don't, like, if you're in a cloud setting, there's only one model, so you don't have to really have to have a model registry for every use case. But you do have to store the whole data set. And whenever you want to make a prediction, you have to kind of load the whole data set and the whole big model. And that's bigger than a traditional model would be, and it's slower to do. And so there are several ways you could potentially get around it. And sort of this whole work was inspired by basically sort of addressing this shortcoming of the original TabPFN architecture, that prediction is slow. Again, tune plus train prediction is fast, train plus prediction is fast, just prediction slow. And I think that's also some of the feedback that Frank got from sort of the internet. But in particular for me, like working at a cloud provider, it's something that we care about, is like deploying models. And so we really wanted this to be fast and competitive for this to be useful. The other con was that in the original work, I think it's cited to be up to 2,000 rows. I think now it's higher, but generally there's a quadratic dependency because of the attention mechanism. We are not addressing this here. This is sort of the other thing that for the settings that my employer is interested in, is kind of limiting. So I mean, 2,000 rows is great for a lot of settings, but if you work on like huge databases, it's very little. It would be great to use this in all settings. So then, so ideally I'd like it to be like 2 million rows, but yeah. With the work with the MotherNetwork, though, what we are addressing is if the test set is very big, we're much more efficient in TabPFN. So that's like one step, but training is still quadratic. Okay, and so from a very high-level viewpoint, we try to get the best of both worlds, meaning the best of the classical, where we have very fast prediction, and the best of TabPFN, where we have very fast training. And so we do the meta training of TabPFN, but instead of, we create this MotherNet architecture, which is a hypernetwork. Then if we get the training data, we do in-context learning. This in-context learning will create a prediction model, which in our case is a small neural network. And so this is a very compact representation of the prediction function. And then once you get a new test row, you can use your standard prediction on a small MLP, which is incredibly fast, and you get predictions. And so I think I'll spend most of my talk now that I have left on this slide, which is the architecture. Unfortunately, I didn't have time to make many, many more slides to give you all the details. But so in a sense, on the left-hand side, you have the transformer blocks, which are essentially the same as in TabPFN. So you have your training samples, X's and Y's. They get linearly projected into an embedding layer, which is like 512 dimensions usually. And I think the one difference that I do to TabPFN, and I haven't really done a good ablation on this, is that I one-hot encode the targets, whereas TabPFN just does a one linear prediction. So you have one D embedding of all the labels, where I have a number of classes, many dimensional or rank embedding into the first embedding. You do your transformer, and then in the end, I summarize them to do using a multi-head attention with a learned query to get some summary. This here you can think of as, and this is kind of crazy, a summary of the data set. And I think in the current best results, it has 2048 dimensions, but it's actually not very critical. So the whole data set got compressed into this one vector of 2048 dimension. And that's pretty crazy to me, but okay. We take this then and we reshape it into weights of a small neural network. So here I depicted one with one hidden layer. I think the current results are best with two hidden layers. But basically, you just take this vector, reshape it to get the weights of the neural network, W1, W2, and then you you pass in the test set, just say a single row, or your whole test, you're training your whole test set, and then you do cross entropy loss, and all of this is learned during test set loss. So you do backpropagation through this, through this, through this, through everything. And so I'm going to talk about the low rank part here in a second, but it's not as critical. So overall, sort of the light blue is weights that you learn during meta training. The orange parts are things that are per in-context learning. So you pass in a training data set, you get this one activation vector, and you reshape it, and it gives you the weights. And then the light green here are activations per test row. So this is just a standard neural network. And so these are sort of the three different phases and the activations of or the weights and the activations of the three different phases. Okay, questions so far? Anything? Okay, no questions in the chat. So you can change a lot about the architecture. I tried out a bunch of different things. So the one I've depicted here, which is with the low rank of the weights. So the output layer, because there's always 10 classes in the original TabPFN, the output layer always size 10. And so we always create a full rank output layer from the transformer. But for all the previous layers, they're sort of, the first one is 100 times number of hidden units. Number of hidden units is something like 512. So and so if you have, say, two hidden layers, you have another 512 times 512 matrix in here. And so we have this one vector here that is like 2048 dimensional, and we reshape it into something that's like tens of thousands of dimensions, which is these weight vectors. And I figured that might maybe be hard to learn, and also it's a lot of parameters. So basically all of the parameters of this model are in these layers, because the weight matrix going from this, or this dense radial weight matrix is where all the parameters are, because it's like, as I said, like it's 2000 times like 15,000 or 30,000 or something like that to create the weight matrices. And so I wanted to get the number of parameters down and wanted to make the learning more efficient. And so the most obvious thing was to do a low rank version where each of the weight layers is combined of this, what I call the pred part, which is created by the hypernetwork, and the fixed part, which is learned during the meta training, I guess I called it. So you can think of this as learning a bank of weight matrices during the meta training, which are then combined using sort of the other half of the low rank factorization that comes from the transformer model. And this way you cut down drastically on the number of parameters. I'm now using in, I think it's 512 hidden dimensions, but the rank is only 32. In the end, so because the experiments take quite a long time, so somewhere between 1 week and 4 weeks to get full accuracy, I haven't done, and the training is a little bit unstable, so you would have to do many runs to get very precise like estimates. I haven't really done the proper ablations that I would like to do, but sort of doing the low rank, I think, is like slightly faster, but it's not, this is not what makes it work or not work. For a long time, I thought the reason why I had this learned query here is so I can control the dimensionality of the output of the dataset embedding here, independent from the size of the hidden layer in the transformer, which I thought was nice. So I could like put more capacity in this decoder stage and make the bottleneck a little bit less big. Turns out that actually doesn't really help. I now did, I used, I think here's a, I don't know if there's Amazon folks here, but I actually started using oh my God, the Hypertune. It's called Hypertune, right? No, SineTune. Sorry, SineTune. Yes, I started using SineTune a lot now after I saw Cedric's. No, not Cedric. Matthias gave the talk. Matthias gave the talk, and I was like, oh my God, this is amazing. This is just what I need. And so now I'm using this heavily. And it kind of turns out that a lot of the parameters I set didn't really matter so much. I get many good configurations with different setups. And so, yeah. And I didn't put in any of the curves, but I get all these cool SineTune curves of like when it starts, when it stops, and so on. Anyway, so you can also do something that's more like, I think was called prefix tuning, more or less. Well, or similar to that, where you put the query in the input layer. So you have a special token in the input layer, it's sort of like your classification token or something like this, and you pass it through transformer. SineTune says this is a little bit better, actually. Then I'm fixed. I still have I have the same dimensionality everywhere, which is 512, and I don't have, the architecture looks a little bit different, but basically I just take the activations in the sense of the last token, which is the sort of classification token, or here in this context, you could say it's the hypernetwork token or something like that. That is also learned. Also, with SineTune, I found also you can see, I don't know if you were here. So it's 7 a.m. for me, so that's why I confuse all the names. So this was three names I blanked out of. I apologize. Anyway, so the hidden dimension also doesn't seem to matter that much. So I have well-performing stuff with I think down to 128. And so I'm using 12 transformer blocks in the paper, but I think ScienTune usually finds something between 14 and 19 or something. There seems to be a lot of randomness in this. So like the paper has one architecture, and these are the results that were the best. I'm actually not entirely sure how I'm going to move forward. If anyone has any good suggestions how to report the results of a very sort of unstable Bayesian optimization, where the architecture, like a lot of architectures seem to work. I'd be interested to hear what people think about that. Okay. We can come back to this later for discussion and questions, but it's in principle, it's very simple. And the shocking part is that it works. So, okay, actually, I'm gonna skip this, I think, but I'm just gonna show you some results. So I'm reporting results. First, I'm going to show you the test set from the TabPFN paper, where I'm including all the data sets, not only what was called numeric data sets. So this also includes data with missing values and data with categorical values. And oh, the other thing that I should have put a slide in is NLP distill. The other way that's kind of obvious to get around this slow prediction time of TabPFN is to distill TabPFN per data set. And I'm not aware of anyone having done something like this. But then on the other hand, I'm not aware of anyone doing something like TabPFN before, so it wasn't really meaningful before maybe. So what we're doing for this is that we take TabPFN, we produce probabilistic outputs on the training set, train a neural network on the training set, an MLP with like 2 hidden layers, something very simple again. And then we get a fast prediction time that's, yeah. But we spend a little bit more time during training because we have to train this neural network, small neural network, using gradient descent from the output of TabPFN. Maybe I should have emphasized there's no in-context gradient descent. There's no gradient descent ever done on any real data. We never compute a gradient on any real data, which is bananas to me. And which says, wow, the prior that Frank's team came up with is actually really good. I'm later going to criticize the prior, or the first version of the prior. Now they have a much better one. But that this works is completely incredible to me. So this creates a neural network on real data with any gradient ever computed on any real data. Okay, whereas NLP distill does gradient descent, does like standard learning, but as teacher, it uses the training set outputs of TabPFN. And so this is, I found there quite a big discrepancy between the test set and the validation set. So the test set is a subset of the CC18. The validation set was collected, I think, by Sam and Noah from OpenML. That's not CC18. And so I think the validation set results make more sense than the test set results, but I'm going to show you test set results because that's the test set. I'm comparing for the baseline methods like MLP, random forest, logistic regression, XGBoost, and KNN. These are all with 1 hour of tuning time. So we run the same hyperparameter search space as Frank did for MLP. They didn't have a standard MLP. They had the more complex regularization cocktails, I think. So this one I made up I think is kind of reasonable. And so this is the average ROC AUC normalized, so that for each data set, it's between 0 and 1. So you can see, so we also trained TabPFN, which is like sometimes a little bit better, sometimes a little bit worse than, but it's mostly the same as the original one. On average, they both beat XGBoost. So what I found interesting here is that MotherNet is better than the MLP. So this is an MLP with an architect. This searches over the architecture, learning rate, and everything for an hour. This has never done a gradient on a real data set. And here, actually here we fixed the architecture, fixed learning rate, everything across all the test data sets, and used TabPFN as a training algorithm. So in a sense, ideally, I would like MotherNet to be the same as TabPFN. On the test data set, it's not the case. On the validation data set, which I've shown in a bit, it's got actually much closer. And but you can see also on this data set, MotherNet is not as good as doing gradient descent with the teacher. This is actually, I think this is incredibly good. So what you can see from this MLP distill being quite good. So I mean, is that TabPFN really learns a good regularizer, because we're just taking the training set, and the training set outputs of TabPFN, and that's an incredibly good teacher. We're not taking a separate validation set. We're not doing any augmentation. Just the probabilities on the training set are so way better than trying to tune per data set the architecture and regularization and doing dropout and whatever. So this is really, really interesting to me, is that TabPFN learned such a good regularizer and can be distilled so well. The other thing that I saw is, so this is averages, this is ranking critical differences, and you can actually see they look very different. So you can see that MLP distill is ranked slightly higher than XGBoost, but they're all in an equivalence class. And if you take out our TabPFN, then MotherNet and XGBoost, MLP distill, and the whole TabPFN are all in equivalence class. Again, so the reason I don't trust this test set is because random forest is worse than logistic regression. And that seems a little bit strange to me. But, you know, I'm going to zoom in a little bit more in some results later. But my main takeaway is like, this works to a pretty, like, statistically indistinguishable from XGBoost is pretty good for something like as a proof of concept. That's I think that's already a pretty good result. Should you use MotherNet in the form in the paper? It's probably not to production ready, but the method overall works, and I think that's incredible. So the real reason why we did this is get faster predict time in TabPFN, and so here I have speed ups compared to XGBoost if you look at predict, fit predict, and tune. So if you look at the prediction time from TabPFN and at XGBoost, this is XGBoost on a CPU. So TabPFN takes about 5 times as long on average. This is on the test set. 5 times as long as on average for prediction. It's 40 times faster if you look at training plus prediction. If you look at training plus tuning plus prediction, it's 300 times faster. If you now look at MLP distill, it's so that's the distill version. It's actually 20 times faster than XGBoost, which is incredible. Fit plus predict time basically is as same time as XGBoost, and fit predict and tuning time 8 times faster. So basically, doing the gradient descent to do the distillation, we lose all the speed benefit in fitting that we had from TabPFN. Whereas if you look at MotherNet on GPU, prediction time is now 4 times faster than XGBoost. It's a little bit slower than MLP distill because we're using an ensemble of 3 hypernetworks, similar to how TabPFN works, whereas the MLP distill is we ensemble the TabPFNs and then train a single MLP. So it's like, yeah, a little bit more than 3 times faster. Actually, it's 5 times faster. But if we look at fit and predict time, because there's no gradient descent whatsoever, we're nearly as fast as TabPFN on average. If the test data set gets large, we're actually much faster than TabPFN. So if you have a training set of size 1,000 and a test set of size 10,000, we'll be much faster than TabPFN. On this data set, it's a 50-50 split on small data sets. So we're pretty comparable. And fit predict tuning is also pretty comparable. You might say it's unfair to do GPU versus CPU times. So I also give you the CPU times. But yeah, I'm not trying to say this is faster than XGBoost really that much if you run on CPU, but it's definitely in basically the same ballpark. And I think you can get bigger wins on the neural net architectures than you could get on XGBoost if you run on the GPU.
I think also XGBoost is heavily optimized, right? The code to run really fast.
Yes, sure. I mean, this here is me hacking together some NumPy code in 3 weeks or something, and this is 10 years of people hardening it. So it's not so bad. I mean, the results are not. So again, the results are not like constantly better. Don't throw away XGBoost yet, but I think this is working to a degree that is surprising. It's my takeaway. Okay, now is a good time to tell me why this doesn't work. Otherwise, I'm gonna jump into a little bit more detailed analysis of some of the results. No questions? So usually when there's no questions, you lost everything. But I know that at least for this audience, for some people, everything was clear because Frank already knew all of this. And so there's at least one person for whom everything was clear, Leonard probably also, and I only potentially lost all the rest.
Okay, I pasted some questions into the chat. You can choose which to answer. I can read them. So the first is just a comment, like you said you use SignTune and you have all these different networks and they all work. You could just put in an ablation section saying, oh, look, all these work, right? That would be very helpful to the reader, I think. And yeah, I don't know any silver bullet of how else to do this, but that itself would be very useful.
So how would you present the ablation results? Like, I mean, I don't have a systematic like test with this and without this because there's only single runs with each hyperparameter setting, right? And the runs might exhibit a lot of variability.
Yeah, I think probably just present the raw data.
Yeah, okay.
It is much better than people going and saying, oh, this is my result and hiding the 20 tests they did. And so I think that's useful. And yeah, since the individual runs are so expensive, you probably don't have thousands of runs. So it's, yeah, I mean, maybe just as an online thing, like a CSV or something.
Yeah. I think I have I have thousands of runs because it's using like a, oh my God, it's really too early here to do this. No, it's okay. It's using multi-fidelity, right? So most of the runs are incredibly short. I could filter out only the ones that are sort of long enough to be interesting.
Yeah, I don't know. Aaron, does the SignTune have any report feature?
Yeah, totally. I mean, we save all the results in the CSV file, but what you could do is essentially what you just said, right? Fit out all the ones that survived until the end. And then if you have a Bayesian method, so a simple approach would be just to plot the sampling distribution. And then you usually see a pattern that it samples around the good region, right? So that gives you a sense of where the good regions are. And if that distribution looks like a uniform distribution, then essentially that means that everything works. That would be the most simplest way, I think, to plot the data.
To plot 15-dimensional space where most dimensions are categorical.
Well, yeah, I mean, well, you would have them 50 plus. Maybe you can trim it down to the most important one, the most interesting ones, right? So, I mean, you could also just feed that into tools like FNOVA, so Fang's tool, for example, which I think also has a multi-fidelity version now. That's something you could also do to get a more statistically reliable way. I personally look at the sampling distributions because they're most intuitive. And yeah.
Yeah, I don't know the output format of SignTune, but if you could feed it into DeepCave, there's all kinds of different visualizations.
Yeah, it's just a CSV file, right? So you can just pass a CSV file or the pandas data file.
I also actually have everything in MLflow as well. I have double logging.
Cool. Yeah, when you're ready taking notes, I can.
Oh, yeah.
The MLP distill, does that use the same architecture as a MotherNet?
I think it's less wide right now. So basically, I did a rough search, not a very fine search, because I thought it was. I mean, it seems like actually from a practical perspective, it seems very good, but from a theoretical, it was less interesting. So I didn't. But I think it has 2 hidden layers, and you're now seeing me looking at GitHub, right?
Yeah.
Sorry, I'm trying to find my.
It's good advertising for DeepCave.
DeepCave, amazing stuff. But I should have my presentation open in somewhere. There. Okay. Yeah, it's similar. I think I'm not sure if it is 512 hidden units or 128. It's pretty small. I did some the thing is, again, it's surprising that picking one architecture, one learning rate, one everything works across all the validation, all the test set reasonably well. You can probably get better if you do per data set tuning of the hyperparameters in learning, which would make learning slower again. Is it better to tune the hyperparameters of the distillation algorithm or to tune the hyperparameters of XGBoost? Depends on how much better than XGBoost we get. If we get really good results with TabPFN, maybe we want to just tune the distillation process and not tune the original. But so from a practical perspective, you could do a lot more there. But yeah, generally the architectures are all very simple. Densely connected MLPs, no shortcuts.
Yeah. No, I'm basically asking because if the MLP distill is doing a really good job, then that's sort of the upper bound that the MotherNet with this particular architecture for the child network could get. But probably this is not even the upper bound yet, right? Because it doesn't have optimal hyperparameters for each data set and so on. So you could even potentially hope to even get better with this architecture in the end.
And there's data
Then
sets
MLP
where it
does
is. I'll show some examples. Like
okay.
none of these really dominate. It's interestingly, none of these really dominates any of the other ones.
And then I had a question about the inference speed here. So I fully agree that original TabPFN was very slow at inference time. I'm actually somewhat surprised that it's not even a lot slower. So it's only 5 times slower than XGBoost here. Was this XGBoost default? Was there any assembling of TabPFN? Because we worked a lot on making it faster because we thought it's like hundreds of times slower. Not like
something a detail that I left out is that all of the transformer-based things use an ensemble of size 3. We reported results with an ensemble of size 32 mostly, I think. So yours is just 10 times slower than what I'd say. I mean, that's one aspect that makes it 10 times slower. Might also be that I have faster GPU.
32 ensembles is very it didn't help a lot anyways.
Yeah. I might have faster GPUs. Okay, I'm certainly have faster GPUs. These are A100s. But also, this is a sort of, from a deployment scenario, your data set, this benchmark is splitting into 50-50 training test, which if you do data science, it's like you actually made the training set small or the test set very big. If you do deployment, the test data set is very small. Usually the test data set is bigger, actually, like, or than the training set. And so depending on your setting, either it can be better than this or it can be a lot worse than this.
Yeah, sure. Well, and then finally, you mentioned, well, sort of, oh yeah, XGBoost was not run on GPU. We actually tried running it on GPU. That just didn't really get faster. Maybe we did something wrong, but does anyone know how to run XGBoost on GPU? It just didn't work.
Okay, so I once talked with a person that worked on that for a while, and I think he said like 5 to 7x is the ideal. But I have not confirmed that. And so it might be that here, because the data sets are very small, you're not getting any speed up. But I think 5 or 7 is like the upper bound.
Cool, thanks.
Okay. Well, I thought I had way too little slides, but then I talked a lot. Okay, so we don't have that much time left. So here's some validation set results. As I said, they look quite different actually, because MotherNet ranks higher. You can say rank is not really informative, and it's only the bars that count, but MotherNet ranks higher than XGBoost and also higher than MLP distill, which is interesting. And so here the gap between MotherNet and the TabPFNs is much smaller. So one thing that is sort of where I focus in my follow-up work, and I hope maybe the next 2 weeks I can get something there, is that so there's a pretty big difference if you look at the average AUC and the ranking, and that's because there's really big gaps in some of the data sets. So this is from the validation data set, where there's the biggest gap between TabPFN and XGBoost. And so, you can also see on these 2 data sets, MotherNet is as good as XGBoost, and TabPFN is not. And I don't have a good explanation for that, but that's interesting.
Sorry to ask, but do you have any idea whether this have categorical features, those 2 data sets?
These have a bunch of categorical features, but I don't know. I don't think so I'm using one-hot encoding for categorical features, but it actually doesn't make a big difference.
Because that was something we found. Sorry, go ahead, Frank.
Like both your TabPFN and your MotherNet have all the same architectural choices for categorical parameters, etc. Right? So that
Yes.
shouldn't make any difference.
By the way, Monk's one thing that, okay, I haven't looked into this one. Monk's problem, this is actually a synthetic data set that has a very simple arithmetic rule, and maybe it's like, I don't know, 5 times feature 2 is plus 7 is bigger than feature 3 or something like that. It might be that a neural network is better at expressing that, but that's just a completely unsubstantiated guess. But so what I was more interested in was these 3 here at the top. And I apologize to Frank's team who have gotten 10 emails from me about these data sets. So the first 2, okay, parity 5 plus 5. Oh, do I have a visualization? Okay, so this is teaching assistant. So these 2 have data leakage in interesting ways. Teaching assistant, if you plot the ID column, which is included, this was a bug in the metadata in OpenML, this ID should probably be excluded. But if you look at the ID feature, it's very informative of the classes. There's 3 classes. So basically, this is what it looks like. It's chunked. The chunks actually, I think they have, maybe this is not the best visualization, have relatively even sizes, and they're always in this order. So this is really complete data leakage. But XGBoost can make use of the data leakage, and TabPFN and MotherNet cannot. And that's because, at least in the original version, TabPFN doesn't have any high-frequency changes like this in the prior. And so these step functions are obviously very easy for tree-based learners, not very easy for neural networks in general. Actually, if you try to just train an MLP on just this feature, it's going to have a hard time. You have to do a lot of tuning for it to work. You probably need to add some other activation function or do some Fourier stuff or something like that. So in a sense, it's like, okay, this is data leakage, but you could have something where this is not data leakage and you want to make use of this feature, and TabPFN and MotherNet in the current version could not, in the versions that I had. Shizu is slightly different. Here, the IDs repeat. So if you memorize an integer ID, you can get the result. So basically, you have patients, and you have 5 rows per patient, or you have somewhere between 1 and 5 rows per patient. And if you memorize the row ID, which is an integer, then you can predict the target. And so you need, which is also, again, easy for tree-based models. In particular, this is model as a continuous feature, so it's basically impossible for neural networks. Again, this is data leakage, but maybe also we would want to be able to, I mean, this is like a kind of weird thing, so I'm not sure if I want to add this into the prior or not. Being able to memorize large integers. The thing that I found a little bit more interesting is the parity 5 plus 5. Someone, an undergrad friend of mine, actually made this beautiful visualization after I asked how to visualize this data set on LinkedIn. And so basically there's several bits, bit 2. So this is a enumeration of all 10-bit numbers. Actually, 100 rows are duplicated, but I think that's a bug in the data set that's just been carried around for 10 years and no one realized. But the idea is it's all the 10-bit numbers. You selected some bits, bit 2, 3, 4, 6, 8, which are 5, and you compute a parity of them. You can see if all of them are 1, output is 1, and if 4 of them are 1, then or if an even number is 1, the output is 0. If an odd number is 1, the output is 1. You can see this beautifully in this visualization. and then the other ones are just ignored. What's interesting about this is that if you take so there's two things that are hard about this for TabPFN. One is ignoring features, which it couldn't do very well. So if you remove the unimportant features, then TabPFN still fails. But because these higher order interactions are something TabPFN was kind of bad at, and MotherNet is also bad at. And so this is something that I'm also working on adding to the prior. And if you add it to the prior, then actually you can learn this. And I don't have the results on this yet, but basically, if you add Boolean functions to the prior, you can then learn this. The other thing is you also need to add to the prior, I think, that you can ignore that there's unimportant features. In the original TabPFN, there's all the features matter to some degree. So there's no explicit mechanism for uninformative features, and I think Frank's team added that. But yeah, you need to also add that, and then I think you can do well on this data set. Okay, this is boring. I created like families of synthetic data sets to see how, like, if you make functions more wiggly and more step-like, then TabPFN and MotherNet are really bad, and MLPs are even worse, and random forests don't care if you have a lot of steps in a function, which makes sense. If you look at these Boolean functions of higher degree, these parity-like functions, if you increase the rank, well, at some point, if you do a full rank of like 10 over 10-bit numbers, it's impossible to learn. But random forests and MLPs both can learn these much more robustly than MotherNet and TabPFN. But if you add these to the prior, you can actually get, so this is not in this figure yet, you can actually get as good as random forest. So basically, I now focused on trying to close these gaps because they were kind of annoying to me, and then I can go back to trying to close the other gaps. Yeah. Wow, and I made it to time. I talked a lot. Any more questions, suggestions? I see in the chat that I don't know how to pronounce it, gametes maybe is also synthetic, which I wasn't aware of. So synthetic, it's interesting that TabPFN is bad on synthetic data sets. And okay, I'm going to talk even more now. Fun thing is, I found all these data quality issues in the CC18 and the OpenML datasets by looking at where TabPFN is bad at. TabPFN is bad at low quality data. And that was kind of funny. Okay, now I'm gonna stop.